Welcome back to lecture series on aerospace propulsion. So, what we are going to see in this today's lecture is that we are going to see something about combustion chamber cooling and why do we need combustion chamber cooling and what are the different methods we implement to achieve this combustion chamber cooling. And then later on, we are going to discuss about what are all the requirements of fuel which we are going to use for our aerospace application or aircraft application. This is what we are going to discuss in the today's class. Okay. So now let's start with what is this combustion chamber cooling and why do we need that? Okay. As your that name suggests, that cooling, basically here we are trying to reduce the temperature. Okay. So temperature of what? Basically we are trying to reduce the temperature of the combustion chamber walls. You see, in a gas turbine where your combustion process is happening, basically in the combustion chamber, what do? We inject the fuel and we burn it to high temperature in order to add energy to our cycle, right? So in the form of heat, we are adding energy to our cycle so that I can convert this heat energy into mechanical energy when it goes to the turbine. Okay, so before that, the temperature we are basically releasing when we do the combustion of a conventional aviation fuel is that we will get a temperature of around 2000 degrees Celsius. You see, 2000 degrees Celsius means it's very, very high. We don't have material which can withstand this high temperature. So that means what we have to do. So what will happen if you are not going to cool down our combustion chamber? Obviously, your combustion chamber is going to melt, or what will happen? It is going to have the creep problem. You know what is creep, right? See, when we apply a mechanical load, what will happen? Your material will elongate. Okay, when I remove that mechanical load, once again, if the material is within the elastic limit, what will happen? Whatever the elongation happen, it will once again come back. But when you are having the high temperature, what will happen is that, you see, we are doing a combustion and you are having the hot gas. This hot gas is contained within the combustion chamber by liner as well as your casing. So your liner is directly exposed to the high temperature. So since it is exposed to the high temperature, you will have the convection as well as radiation, because here the temperature is very, very high. You will have the radiation. So because of this convection from your hot gas to your wall, that is inner wall, that is basically flame tube or liner, what will happen? The temperature of your liner material will be increased. So when this temperature is increased, what will happen? The material is going to elongate because of this temperature. Okay, so this elongation, suppose if even though the applied load, whatever the mechanical load acting on that particular material is within the yield strength, you know what is yield strength? That is the maximum strength your material can withstand up to the elastic limit. Once you exceed that yield strength, what will happen? You will have a permanent deformation, that is the plastic limit. Okay. So what will happen if you are having the high temperature is that you will have this creep problem. That is, even though the mechanical stresses acting on your combustion chambers are within the yield strength, because of this high temperature, your material is going to elongate more than it will go to the plastic limits, which will cause the permanent deformation. So obviously this continuous cycling or continuous creeping will result in failure of your material. Thus such, we have to prevent this creep problem. How do I prevent is that by cooling down your gas, because this creep is directly proportional to the temperature of your gas. So higher the temperature, what will happen? You will have the higher creep problem. So if I want to prevent my combustion chamber from failure, what I have to do is that I should limit my temperature acting on the walls. That is basically it's a liner or casing. Mainly it is a liner. Okay. So we have to limit the temperature, or we have to take off the heat of your material such that it can be the temperature will be well within the limit, so that you won't have the permanent deformation. Okay. So for that purpose only, we have to introduce the combustion chamber cooling. Okay, so you see the high pressure gas or high pressure air from your compressor, almost 60% of your gas is used for cooling of your flame tube alone. You see, let's say an 100 kg of, or let's say 10 kg of air is coming inside your combustion chamber, means In that you need hardly 4 kg for the complete combustion. Remaining 6 kg of your air is being used for just cooling purpose alone, cooling and as well as dilution of your like a combustion gas. Because you see, after your combustion chamber, you have the turbine. Okay, so basically turbine is your rotodynamic is a turbo machinery. So there also you have to limit your temperature. So for that we use almost 60% of air to for cooling as well as dilution of your combustion gas. Okay, that's why the combustion chamber cooling is very very important. If you want to have a, like, let's say any combustion chamber we will design, it will have something called an hot time. Hot time in sense how much time, hot hours, basically hot hour means basically how much time this combustion chamber is exposed to the combustion. Okay, so based on that, you will have the lifetime of your combustion chamber will keep on coming down as your hot time is being increased. So why is because of the creep problem. So if I want to increase my like life expectancy of my combustion chamber, it should be provided with a proper cooling setup so that you can have a proper combustion chamber. We are going to see what are the different type of combustion chamber cooling we are using. Okay, what was used and what exactly we are using nowadays. We are going to see. Okay, so in the combustion chamber cooling, one of the earliest method which was used something called lever cooling. Okay, so what is this lever cooling? Is that we know that we have a combustion chamber means, let's say this is your casing and this is your liner or flame tube. Basically, liner or flame tube. Within that liner or flame tube only, your combustion gas or combustion will occur or combustion hot gas will be limited. The gap between this liner and casing will be will have the cool air. Okay, so in this cooled air we are having means obviously when the airflow enters inside your combustion chamber, some portion, roughly 10 to 15% of air will enter here, remaining air will be entering in the passage between your combustion chamber, that is casing and the liner. Okay, so first of all, your liner is your casing is protected because we have a cooling air around the entire circumference. So you will not have much of problem for your outer wall, but still you will have the, because there is no direct contact, so you won't have any convection between your hot air and your combustion chamber casing, but still you will have the, because of radiation, maybe the temperature of your outer wall also will be increased, but that we can reduce because we have the cooling air continue to for like move through this passage between your liner and casing, so you won't have any problem with your outer casing. The issue is with the liner or flame tube where the material is directly exposed to the high temperature. Okay, so what is this lever cooling is that, you see, your liner will be fabricated in a form of cylindrical shells. Okay, so through these cylindrical cells, what will happen is that you will send the cold air. So what is happening from your hot gas to your flame tube, you will have the convection problem, and inside when the cooling air is passing through, what will happen? It is going to take away the heat of your liner. So as such, what will happen? Your temperature will not exceed above certain limit, so you can maintain the temperature of your liner to the required value, so that you won't have the creep problem, or you will have what that you won't have the high temperature rise in your liners. Okay, so basically this lever cooling is a kind of a convective cooling where the airflow will be passing through the cylindrical shells. The source of airflow is basically that is the air moving between your liner and the casing. Okay. The next one is something called splash cooling. Okay, so what is this splash cooling in sense? We have the spacing between your casing and liner, right? What will happen at the certain location? The cooling air will enter through the small holes present on this liner. Okay, and they are going to impinge on the cooling skirts or cooling surface of your liner, which is going to basically take away the heat of your combustion chamber. Okay, so that is basically it is going to take away the heat of your liner material so that you can maintain the temperature of your liner. Basically, it is a kind of a combination of impinging cooling, that is, and cold air will impact on the hot surface. Okay, when it is impact on the hot surface, what is going to happen? It is going to take away the some portion of your heat of your hot surface. So in that way, you can reduce the temperature of your liner. Okay, this is a splash cooling. Next one is a film cooling, which is the bit advanced than your previous simple direct convective cooling or splash cooling. What is this film cooling? Is that in the previous cases and all, what we have done is that we are have an hot gas. We have the liner. We have the cold gas. So when the cold gas is passing through, basically it is taking away the heat of your material, that is liner. Whereas in the film cooling, what we do is that we will have the holes along the liner. When the air is entering through these holes, it is going to form a thin layer between your combustion gas, that is hot gas, and your liner. Okay, so what is going to happen is basically they are first of all preventing the direct contact between your hot gas and your liner. So that itself is going to reduce the heat generated on your liner. And one more thing is that as your film cooling, that air thin layer of air is continuing to move, the temperature of your film also will not be increased to very high value. So that's that. Basically here we are preventing the heat or direct contact between your hot gas and the liner itself. In the previous cases and all, that's not the case. We'll have a direct contact between your hot gas and your liner. The liner will be heated up, but we'll send the cold air, which is going to take away the heat of your liner material. Whereas in the film cooling, what we do is that we first prevent the direct contact. At the same time, when the this thin film of air is continuing to move, it is going to take away the heat accumulated on your liner also. That way, this is much more effective than the previous case. Okay. So there are two types of film cooling. One is impinging film cooling. Another one is the convective film cooling. In this impinging film cooling, we'll have a more complication when we manufacture. So most of the time, we use this convective film cooling because it's much more effective than your impinging film cooling. Okay. So what we do is basically we have the convection. Controlled convection in sense, when the thin layer is forming, what is happening is that the heat transfer between your hot gas and your liner material is reduced. Okay, that way we are able to convert the heat transfer rate. So as long as we control the heat transfer rate, that is convective heat transfer rate, you can prevent the liner from heating up. So that way you can increase the life expectancy of your combustion chamber walls, that is a liner wall. A last one, which is like most advanced type or most of your combustion chamber nowadays, they use the transpiration cooling. Okay, this transpiration cooling is much more effective than the other cooling technique, as because it is capable of reducing the almost because here why I said that this transpiration cooling is much more advanced and mostly used is because the amount of air required for the cooling purpose is reduced by 50%. Let's say previously we needed 10 kg per second air is required for cooling a combustion chamber. When we use this transpiration cooling, you need only 5 kg per second. So you could say how effective this transpiration cooling works. So what is this transpiration cooling in sense? You will have the liner wall, basically where they are porous walls. Porous wall means they are that micro holes you will have. Through that micro holes, your air will be leaking through, and it's kind of similar to your film cooling, but it's bit more advanced where the barrier is much more effective in case of your transpiration cooling. So you'll have a small porous holes. Through that, your air will be entering, continue to enter, and it will form the barrier between your combustion gas and your wall. So that way, it is going to prevent the heat transfer between your hot gas and your liner. Okay. We are going to see another term which we call it as the effective cooling. So what is this effective cooling? We have seen different types of cooling, right? So how do I find out which type of cooling is working better? So for that, how do we find out is that we have something called a parameter called effective cooling. So what is this effective cooling is that which we call it as the pi. Basically, it is the ratio between difference in the temperature between your hot gas and the material divided by the hot gas and your cold gas. So what is your Tg here? Basically, that is the hot gas temperature, and Tm is the what is the average temperature of your metal. Basically, that is the liner surface, and what is your Tc is the cooling air temperature. Basically, that is the temperature of your air coming out of your compressor. So Tg minus Tm is the difference between how much temperature, what is the temperature of your hot gas, and what is the minus what is the temperature of your metal or the surface of your liner divided by what is the difference temperature difference between your combustion gas and the cold gas. So this ratio what we call it as the effective cooling. So from this I can find out which method is more effective in providing the better cooling for your combustion chamber surface. We say this is the graph which shows for the different types of cooling technique, how much amount of percentage of air we require. Okay, so let's say we have a kind of simple film cooling, that is the oldest type of cooling which they have used. Okay, let's say if it is going to use 100% of available air, when I introduce the impingement cooling, they are required only around 80%. Okay, that means your impingement film cooling is better than simple film cooling technique. The next one is the convective film cooling. Convective film cooling, which requires hardly 70% of the total air. That means this is even better than your impingement cooling. That's what I said previously. Comparing the film cooling of your impingement and the convection film cooling, your convection film cooling is better because it requires less amount of air. The next one is impingement plus film cooling. So both if I am going to combine, which is going to create or which is going to record even lesser amount of gas. You see, we need hardly 50% of air required by your simple film cooling. The last, at least, is the transpiration cooling, which is what we are nowadays using in most of our gas turbine combustion chamber, which requires hardly 20% of air required by your simple film cooling. Okay, this transpiration cooling technique is more effective in taking away the heat and more effective in the forming barrier between your hot gas and your cold gas. Okay, so this is all about the different types why we need the combustion chamber cooling. What are the different types of combustion chamber different types of combustion chamber cooling we are using, and how do we measure the effectiveness of a particular method. So you see, you can take any method, you can introduce any new technique also, but how do you find whether it is better than the existing cooling technique or not? By finding out this pi, you can find out whether they are effective or not. Okay, so, and this is the graph which is showing the like how efficient the transpiration cooling technique has been compared to the other techniques. Okay. So next, we are going to discuss about the what are all the requirements of an aircraft. Okay, it's not like your automobiles where we have fuel which can be used any type of fuel. We have a diesel engine, even we add a crude oil engine, right? But when you go for an aircraft, the requirement are very severe, because you see there are so many different parameters this aircraft fuel has to satisfy if at all we are going to use this. Okay, so what are all these requirement of the aircraft fuel which you need to satisfy if I'm going to use it for the aviation needs? First is based on the operation requirements set by the aircraft and the engine. So based on what type of aircraft and what type of engine we are going to use. And first and foremost thing is that it should be low cost and high availability. Okay, low cost and high availability in sense the fuel should be readily available in the market. At the same time, the price should be less. You see, when you take an operation of your aircraft, almost 34% they are using for the labor cost. Next to labor cost, what is the uh, most amount they are spending on an operation of the aircraft is your fuel. It requires almost 17%. Let's say if I'm going to use 1 lakh rupees, okay, not it's just I'm telling you now. Okay, in the 1 lakh rupees, 34,000 is just going for labor cost, and next is almost 17,000 they are spending for the fuel alone. So that means you could see the effect, because if the fuel cost is higher and higher means the operating cost of your aircraft also going to increase. So at the same time, the availability, even a particular fuel is low cost, but if the availability is less, because you see we have thousands and thousands of aircrafts are flying all around the world, so the fuel which is needed should be readily available. There should not be any scarcity of your fuel such that your entire operation of the aircraft is going to become stagnant. Okay, that should not be the case. That's a very, very important point. Low cost and high availability. And next is the low fire risk. Okay, low fire risk in sense, first of all, the inflammability or flammability of your fuel should be less. Okay, that is catching of fire. It should not be like volatile, so that when, so let's say when your aircraft is going to land, let's say during a crash landing, okay, if they are more volatile, means what is going to happen? They are going to easily catch fire, so which we don't want. So the fuel should have the low fire risk. Basically, it implies low vapor pressure. So what is the meaning of low vapor pressure? Is that it's the tendency of your fuel to readily convert from a liquid phase to a vapor phase. It should not easily convert into vapor phase. Okay, if it is converting, in what is going to happen? Your fuel is basically highly unstable, and it should be low volatile, and it should have a high flash point. High flash point means basically the combustion or catching of fire should occur at a high temperature, because if it is occurring at low temperature, what is going to happen? Even a less temperature will tend to catch fire. Means during a crash landing and all, your aircraft is going to easily catch fire. So it should have a high flash point and high conductivity. Okay, high conductivity in sense how easily they can conduct the electricity. Okay, usually the conventional aircraft jet aviation fuels, they have the low conductivity, that is naturally existing aviation fuel. What they will do is that they will add the sediments, external particles to your fuel, so that they will increase the conductivity of your fuel. So which why we need is because when you are fueling, the static electricity which is generated will be easily conducted, such that you will not have the what is it, fire risk problem. So for that, we artificially increase the conductivity of your aviation fuel. Okay. Next is that high heat content for maximum range and pay. In sense, let's say if you are having a different fuel, heat content means that is hardly most of your aviation fuel have the heat content value of 42 megajoules per kilogram. Is the heat release value. So the fuel which we are going to use should have a very high heat content, so that the amount of fuel I am going to store in my aircraft will be less. See, if the heat content value of my fuel is less, means what does that mean? I need to store more amount of fuel if I want to increase my range or payload. Or what will happen if the heat content is less, means your payload will be reduced, because mostly you will be carrying fuel alone. Your aircraft is going to simply fly. So if you want to increase the range and the payload, what you have to do is that you have to select a fuel which is having a high heat content, and next is the fuel should have the high thermal stability. So what is the meaning of high thermal stability? Is that when the temperature is changed, it should not easily oxidize. Okay, when oxidation usually happens, what is going to happen is that it is going to form the jelly-like substance inside your fuel, which is going to block or it is going to block your fuel filter, or it is going to stick on your walls, it is going to make it difficult. So the thermal stability of your fuel, even the temperature change is significant, there should not be much of oxidization, so that you will not have the problem of the jelly-like substance forming inside your fuel. And you should have the low vapor pressure. Okay, so low vapor pressure means that if the during your high altitude and all, your outside pressure is very less. If the vapor pressure is high, means what is going to happen? It is going to easily evaporate your fuel. Even before burning, the fuel is going to simply evaporate. So which is going to create the loss. So I have to select a fuel such that it will have the low vapor pressure. So I will not have the loss. Next is high specific heat. That is CP value should be very high in order to absorb the heat. Okay, regularly for your air, the specific heat value CP is 1.005 kilojoules per kilogram Kelvin, whereas for your fuels, the aviation fuels, we have at 130 degrees Celsius, we'll have 2.43 kilojoules per kilogram Kelvin. There is the specific heat of your fuel, conventional aviation fuel at 130 degrees Celsius. If I am going to reduce the temperature, the specific heat is also going to reduce. Okay. Next is fuel system required. You see, we have a stored fuel. So this stored fuel is not directly just dumped inside your combustion chamber. Okay. So we need to, when we are spraying our fuel, it should be coming in the droplet form. Okay, that means if I want to convert a liquid into droplet form or atomization, what I have to do is that I should increase the pressure of my fluid. Okay, so that pumping ability, in sense, it is the fuel should remain in the liquid phase. Okay, and it should freely atomize. Okay, that is, it should flow freely through the fuel injector. Atomizer is nothing but your fuel injector. That is the pumping ability. And freedom from filter clogging by ice or wax crystal. That is because of the temperature change. Okay, so there should not be any clogging problem for your selected fuel. And freedom from your vapor locking. Vapor locking means, which is going to prevent the fuel coming to your fuel injector. So that is going to cut off your combustion chamber. So that should not be the case. And high lubricity for minimum pump wear. You see, we are going to pressurize our fuel to very high pressure. Okay, so when I pressurize it, I'm going to use the pump, that is reciprocating mechanism or some other mechanism. So if I'm going to use the reciprocating mechanism, the lubricity of your fuel should be sufficient enough so that it can reduce the wear and tear. We can't use a different lubricant over there because the fuel itself will be used as a lubricant. So the lubricity of your fuel which you selected for your aircraft, it should be high enough to prevent the wear and tear. Next one is the combustion chamber requirement. Okay, so what is the combustion chamber requirement? First of all, your fuel should be free from contaminants that is going to cause the blockage of your fuel nozzle or fuel injector. Your hole in the fuel injector is very small. If you're having the external contaminants, what is going to happen? It is going to block your passage, which is going to prevent fuel coming out. And next important thing is that it should have the good atomization characteristic and rapid vaporization. So atomization sense, when I inject my fuel, it should form a uniform droplets, and this uniform droplet should rapidly vaporize. You see, we have a fuel in the liquid form. When I inject, it is in the fine droplet form. Why we are injecting the fine droplet form? I should mix my fuel with the air thoroughly so that I can have the complete combustion process. So when it will happen is that the atomization characteristics of your fuel should be good, and once it atomized, it should rapidly vaporize or dissolve with your air so that it can thoroughly mix with your air. Okay, and another important requirement is that minimum carbon formation. Okay, so that is the freedom from coke deposition. Carbon formation is coke means basically it's a layer of incomplete combustion product which is going to deposit on the combustion chamber walls. You see, we are using a transpiration cooling, right? If you're having the coke deposition means what is going to happen is going to block your inside liner walls, which is going to prevent the cooling air coming through this porous wall, which is going to reduce the effectiveness of your cooling technique which you are going to use. So obviously the fuel you are selecting should be free from coke or carbon formation. Okay, so that is what I said, and a relatively small amount of ash. You see, we are burning a huge amount of fuel, right? So when it is creating ash means it is going to create the environmental effect. So whatever the fuel which you are going to use, you should have the less ash generating capability. Freedom from alkali materials such as sodium. Okay, so what is going to happen if we have the sodium? When it is going to combine with your sulfur, it is going to form the corrosive sulfates, which is going to once again affect your environment. And freedom from vanadium, basically this freedom from vanadium in sense, this is also related to your environmental effect. So these are all the requirement of your fuel which it need to satisfy if I'm going to use it for my aviation purpose. So what we have discussed today, we have started off with why do we need the combustion chamber cooling and what are the different types of combustion chamber cooling we are using, which one is being recently used and different combinations, and we have seen what is the combustion chamber effectiveness, and then we have seen the effectiveness of each and individual technique. Later on, we have discussed about the what are the different requirements of your aviation fuel and what are the conditions it should satisfy if I'm going to use a particular fuel for the aviation application. Okay, so with this, I'll complete this lecture.
Like, share, and subscribe. Hit the bell icon for more updates.